Alrighty. Sounds like it's on. Hi, I'm Michael Ballantyne. I'm a PhD student at Northeastern University. This is joint work with Mitch Gamburg and Jason Hemann. They're also here, so you should chat with them as well. So this talk is about a new way of implementing internal DSLs, and why I hope you'll be excited about it is that it's one way to escape sort of the usual trade-off that we have to make when choosing an implementation technique for an internal domain-specific language. So if sort of these four on the left are our desiderata, if we want to create a DSL that has an optimizing compiler and maybe has a custom static semantics, something that we can't embed in the host language static semantics, then sort of the straightforward way to do that is usually to use a deep embedding or maybe an external DSL or a language workbench to help us implement our DSL. But on the other hand, if we want a DSL that has extensibility of some sort, user extensibility in particular, or if we want to be able to easily intermix DSL code and host language code in our general purpose language that we're embedding in, then a shallow embedding or a conventional macro system of the kind you have in a Lisp, for example, those techniques for a DSL implementation usually give us these desiderata most easily. So what if we want all four of these things at once for our DSL? How do we get that? So I'm going to show you one particular answer, which is a new kind of macro system that I'm calling a multi-language macro system. And it takes ideas from conventional hygienic macro systems, from language workbenches, and particularly the kind of semantic meta-languages that language workbenches provide, and also some sort of ideas from multi-language semantics about how to structure the interaction between different languages. In this case, the host language, like Racket in my context, and the DSL. So my particular implementation of a multi-language macro system is a layer on top of Racket's existing macro system that I call syntax-spec. So that's the system that I'm going to be using today. And in order to illustrate this, I'm going to walk you through sort of the benefits that we're going to get for a particular concrete DSL implementation. So I need to take a moment to introduce you to the DSL that I'm going to use. So the DSL is miniKanren, and it's a very minimal logic programming language. As far as you need to understand today, the essential aspects are that it's logic with equations over tree data, the kind of data that you have in a Lisp, so lists, symbols, forming trees, untyped trees. So we have equality constraints, that's the double equal sign. And then we have some basic logical connectives. So logical disjunction, logical conjunction, existential variable binding, which we call fresh. So on the right is an example of a relation in this language and a query of that relation. So the relation is a predicate that checks whether its argument, or holds when its argument, is symbolic data that looks like a piano numeral. So when we run and we query this relation, we ask for 3 values that satisfy the predicate. And so we get back 0, 1, and 2 expressed as piano numerals. And if we look at the definition of the relation, it's a logical disjunction between one alternative is an equality constraint, that the number is the symbol z representing 0. And the other alternative, we have an equality constraint that the number is a list structure whose head is the symbol s, and the rest is the logic variable m, and we make a recursive call to the relation with that. So it's this recursive logical formula. So if this is our DSL, I want to start by explaining sort of what I mean by the particular desiderata with respect to this DSL. So the first is, what does it mean that we want to be able to have a compiler, an optimizing compiler, for this domain-specific language? So if we have this logical expression in miniKanren, so we existentially bind the variable x, and then we have a conjunction between 2 equality constraints. So the first equality constraint is that x must be the same as the list with the logic variables y and z. And the second, that x must be the same as the logic variables 1 and 2. Well, we can deduce, very trivially, that that must mean that y is 1 and z is 2. And because we're sort of in this existential binding, we know that we're not using the variable x anywhere else. So obviously, a smart compiler could simplify this for us And we really like to optimize to just the conjunction of the basic quality constraints. And this is something that if we are sort of realizing this DSL by turning it into Racket code, host language code, this is an optimization that by the time we've done that compilation, there's going to be too much other junk that there's sort of no hope of the host language optimizer doing this kind of thing for us, right? So this is a place where we need to be able to implement these kinds of domain-specific optimizations that aren't going to be something that a host language compiler is going to be able to realize for us. We want to be able to implement that custom for our DSL. All right, so that's the first property. So the second property is that we'd like our DSL to be extensible. So that first relation that I wrote, admittedly, it's sort of a lot of verbose code for doing something very, very simple. We're functional programmers in this room. We're used to things like pattern matching. So we would much prefer to be able to write that relation with a pattern matching form, right? And in the logical context, that pattern matching form is really going to mean exactly the same thing as these logical connectives. It's going to de-sugar into those logical connectives. But we'd like to be able to define this extension. And really, we'd like users of the language to be able to define such extensions themselves. So that's sort of our second desidera. So third is places where we want to interact between the DSL and the host language, or maybe even other DSLs. So here's a different problem that I'm solving with a relational program. I want a relation between different places that I can get to with flights in an airline network, with multiple direct flights. So the route relation is basically going to be the reflexive transitive closure of the direct flight relation. And the route relation is very nice to write as miniKanren code. It's this recursive logical formula. So that's nice to write in the DSL. But the direct flight relation, if we're thinking about a real airline network with thousands of flights every day, and it's changing all the time, we don't want to like hard code that in DSL code. That doesn't make any sense. Obviously, what we want to do is we want to access some kind of real database of a real flight network. And the problem is that our little DSL obviously doesn't have, a SQL extension necessarily. So what can we do? Well, this is a place where we want our DSL to be sitting in the context of some general purpose language, in this case Racket. And we want to be able to mix DSL code and host language code in sort of an easy way to write this program. So here I'm putting the host language code in red, the DSL code in blue, and the sort of boundaries that mediate the interaction between the two, those are the forms in black here. And so as I said, route is just going to be miniKanren code. I'm omitting it here. But the direct flight relation is going to escape into host language Racket code by using that sort of explicit boundary. And it's just going to make some function calls available from Racket's database library. It could also use another DSL. It could use an SQL DSL in Racket. So this is sort of our third desideratum of what we'd like to be able to do when we implement such a DSL. And this multi-language structure with sort of the explicit boundaries is inspired by Matthews and Findler multi-language semantics. And it's going to turn out that having sort of these explicit boundaries and thinking in this multi-language structure is going to help us sort of both allow interaction with the host language to do things like this, but also be able to implement an optimizing compiler sort of safely. So if we want all of these three things, but we know that sort of with the most typical implementation strategies, we're not going to get them, what's the new solution today? And that's the multi-language macro system. So I have to take just a step back from that for a moment to say sort of what conventional macros are so that we can draw a contrast, right? So if we were to implement the miniKanren DSL with conventional macros, what we would do is we would write a bunch of individual macros. So a macro is a definition of a new syntactic form by transforming it into an existing syntactic form, syntax to syntax transformation. And so we could implement miniKanren by defining a macro for each syntactic form of miniKanren. So for example, we could define a defrel macro to define a relation definition, and it would work potentially by compiling to a Racket procedure definition, right? And then the overall compilation of our program would be a series of such individual steps. So it would look a bit like this. So each individual syntactic form is separately compiling, and we're sort of proceeding outside in. You can see from the colors here where the DSL code is incrementally turning into host language code. And that's sort of how you might implement a DSL with a conventional macro system. But the problem from a perspective of wanting to implement an optimizing compiler is that no one of these macros is getting a complete view of the DSL syntax. They're only looking at their one little fragment, right? So we need a different expansion structure if we're going to be able to sort of get that optimizing compilation in addition to everything else that we want. So here's how a multi-language macro expander is going to work. So the first step is kind of like conventional macro expansion, but only for macros that extend the domain-specific language, not the ones that define the core of the domain-specific language. So things like that pattern matching extension that I described earlier, those are going to expand in sort of this conventional macro expansion step. But once we get down to the forms that define the domain-specific language, not our host language forms, but the ones that define the DSL, then we're going to wait until we get down to all of our code is in the core forms of the domain-specific language. And then we're going to do a compilation step that is a more traditional compiler. And at that point, we know that we've sort of desugared all the syntactic sugar, all the extensions. So we know that our sort of conventional compiler that we're going to write here doesn't have to worry about extensions, right? It can work on a fixed small core language, right? And in this case, the sort of fragment, the size of the fragment that we're going to pass that compiler is the region delineated by the boundaries of the multi-language. So in this case, an entire relation definition at once is going into that compiler, and it can do optimizing compilation on that entire relation. So one thing I want to note is this is just the architecture of extensible general purpose languages like Racket or like Haskell with template Haskell, right? You have an optimizing compiler for a fixed core language, and you have some sort of extensible elaborator on the front end. And we're just lifting that architecture up to domain-specific languages. So in order to lift that architecture to domain-specific languages, the implementation of this expander has to know about the structure of the core language of the DSL. So that thing that has equalities and disjunctions and DEFRELs but doesn't have matchy, right? We have to specify something about that syntax in order to be able to implement this expansion process. So that's where the sort of inspiration from language workbenches come in, is that we are going to have a domain-specific language, a meta-domain-specific language, for specifying the structure of that core language. And it's going to include things like grammar and binding structure and the language boundaries. So in this particular example, highlighting just the part about the grammar, so we're saying that there's a new grammar non-terminal called a goal, or a new syntactic category. And that's separate than a Racket expression. So if you tried to use a Racket expression where a goal is expected, that would be an error. We're extending the syntax of the language. So that's the grammatical part. The binding structure part, so we need the binding structure information in order to do things like implement hygienic macro expansion and make sure that interactions between the DSL and the host that happen through shared variable names are going to be safe. So we're going to specify binding structure. In this case, that existential variable binding form fresh, we're going to specify that it creates a scope, that a name is bound in that scope, that it's visible in the body. And if you're familiar with the scope graph formalism from Visser's group, then you can think of these things as templates for fragments of scope graphs. So that's the binding structure part. And then finally, we can see the sort of multi-language structure part from the specification as well. So we can see that here in red, I've said that the sub-expression of goal from expression is going to be a Racket expression. And so this is going to be sort of the place where we're going to stop expanding for a while so that we can do compilation, and we'll come back to this later. So that's the structure, and it gives us these three features. But what I think is particularly cool is that when we get all these features together, they interact in sort of mutually constructive ways. So it turns out that if we have an optimizing compiler, then it actually gets easier to write our extensions because we don't have to be as careful about the code that they generate. It's going to be simplified for us. If we have multi-language structure with the host language and we're writing extensions, well, we can take advantage of the expressive power of the host language as well as the DSL to implement those extensions. And if we are trying to do an optimizing compiler, interact with the host, well, that multi-language structure and those explicit boundaries are going to help us make this optimization safe in the sense that no code, including host language code, will be able to observe the difference between the optimized and the unoptimized program. So I'm only going to have time to show you exactly what this means for one of these. So let's take a look at that. So in this example of adding this match-e extension, if we really wanted match-e to just directly macro expand to the handwritten program that we wrote before, it's a little bit complicated to write that match-e macro because like some clauses introduce fresh variables, some don't. So in order to implement the tightest code that we would want, we would have to be careful to write that macro carefully. However, we could write a naive version of the macro that just generates a bigger pile of code, right? And this code is going to be more uniform, so it's easier to generate, but it's large and it's not going to perform as well. But if we know that after macro expansion, we're going to have an optimizing compiler run, then we can rely on that optimizing compiler to do certain things to simplify that code that we generated back down. So we can, if our optimizing compiler does things like constant propagation and dead code elimination, then it's just fine to introduce a little bit of indirection in our macro expansion. So this was an idea that Kent Dybvig proposed for Scheme in his talk about a macro author's Bill of Rights, that the macro author should be guaranteed that the compiler is going to do certain optimizations so that the macro can be simpler. The other two sort of legs of these interactions are in the paper. The details of how we create this multi-language boundary and the optimizations that we do for miniKanren are in the paper. And beyond the paper, we've used syntax-spec to implement a bunch of other DSLs as well. And it's something that's released. You can give it a try. I'd love to have more users. And sort of the final takeaways here is that you can have it all. You can have all of these properties simultaneously. And that at least one way to do it is to have a hygienic macro expansion to a core language defined by a language workbench metalanguage, and to use multi-language structure to mediate the interactions between the language. And on 2 p.m. at Friday, I have a longer talk at the miniKanren workshop if you'd like to learn more. Thanks.
I think we have time for one quick question while the next speaker comes up.
Hi, I'm Paul from CISPA. So I have a quick question about the syntax, because you mentioned you can combine the host language and also your object language. So in this case, maybe you have a DSL, you have a Racket, and maybe some of their expressions are overlap. Their syntax are overlap. So in this case, sometimes we may have some ambiguity issues. If you write a program, you simply connect, you mix up all kinds of expressions in different languages. So in that case, is this really an issue in this framework? And if it is, how do you solve it?
So when you write down that specification of the grammar, you're sort of explicitly specifying where the expressions from different languages are allowed. So syntactically, it'll raise an error if you mix these things up in the wrong way.
Thanks.